So, surely you have heard about irrational numbers, like pi, the square root of 2, or the square root of 5. They are numbers that cannot be expressed as a ratio between two integers. So, for example, 0.5 can be expressed as a ratio, it's 1/2. But you cannot really express pi as a ratio, right? So, is it the most irrational number? How would we even define what the most irrational number is? Well, to answer these questions, we can start by trying to approximate pi using fractions. We already know that pi is equal to 3.1415 and so on, so we can roughly say that pi is equal to 3 plus something else. And since that something else is less than 1, we can say that pi is equal to 3 plus 1 over something, where this fraction equals 0.1415 and so on. If we solve for the denominator, we obtain another irrational value, 7.06 and so on, but then again, it can be expressed as 7 plus something else. And we can do the same thing as before, express the something else as a fraction. And once we solve for the denominator, we obtain the irrational value 15.9 and so on, which can still be expressed as 15 plus 1 over something. You get the idea. If we keep going, we get an infinite fraction, called a continued fraction, from where we can obtain a series of approximations called convergence. If we ignore everything after the first plus, we obtain our first convergent, 3. To obtain our second convergent, we ignore everything after the second plus, the one right next to the 7. Here, we can observe one of the most famous approximations for pi, 22/7, which happens to be accurate to 2 decimal places. Once you get the hang of it, we discover that the third convergent is accurate to 4 decimal places. And we can keep going, but here I want to point out two things. First, notice that the convergents don't always offer an approximation that's better than the last. Second, to get a practical approximation for pi, you don't really need to go any further than the third convergent, so pi is really easily approximated with fractions. And so, the most irrational number is the hardest to approximate. To find our mysterious most irrational number, we first want to notice in the continued fraction that the larger the denominator, like this 292, the better the approximation. So to find it, we gotta go small. Let's call our mysterious number x, and to make it as hard to approximate, we use a continued fraction whose only denominators are the smallest positive integer, 1. Here, we can notice that x is equal to 1 over itself. This observation gives us an equation. If we multiply both sides by x, we obtain a quadratic equation. And since we're only adding positive numbers, the only logical solution we obtain is 1 plus the square root of 5 over 2. This number is known as phi, and you may have heard of it as the golden ratio. Yes, the one that makes that spiral shape. And we've done it. As simple as it is, this is the most irrational number, and I'll prove it to you. Keeping in mind phi is equal to 1.618 and so on, let's start computing the first convergence. The first approximation we get is just equal to 1. The second is 2, the third is equal to 1.5, and soon enough we'll realize it is actually pretty hard to approximate. We have to go all the way to the 10th convergent for 3 decimal accuracy. Phi is a pretty cool number, but here's the best part. See if you can find a pattern in these divisions. They divide consecutive terms of the Fibonacci sequence, so the further you go into the sequence, the better your approximation. So for example, if I divided the 13th term over the 12th, we'd have an approximation accurate to 2 decimal places, and if I divided the 25th over the 24th, our approximation is accurate to 9 decimal places. Let's take a step back and recap what we found out. We asked ourselves, what is the most irrational number? And as we played around with continued fractions, we defined how to look for it, and on the way, we found out some really weird and unexpected connections to concepts that seem totally unrelated. This is what math is at its core. We ask questions and have fun and play with logic to find an answer.